Welcome to the Deep Dive. We're the place you come to get really up to speed on complex stuff, fast. Today, we're diving into something huge that's kind of happening quietly. Battery technology. And look, this isn't just about getting more miles in your electric car. It's bigger. It's about, well, fundamentally changing how we power everything, our whole world. So our mission today, get past the headlines. Really understand these two rising stars. Everyone's talking about sodium-ion and solid-state lithium. We've dug through a ton of research, expert takes, all that to bring you this deep dive.
That's right. I mean, lithium-ion batteries, they've been the undisputed champs for ages, haven't they? Powering, well, pretty much everything from your phone to most EVs out there today. But there's this massive push now for alternatives, things that can solve the current weaknesses. And each new type, each chemistry, it comes with its own specific strengths, its own trade-offs. It's all about tackling issues like cost or where we get the materials or just making them safer. It's moving fast.
Absolutely. Before we get to the challengers, we've got to talk about the current king, right? Lithium-ion. Still number one for EVs, for grid storage, but it's not just one thing, is it? It's more like different recipes, different flavors maybe, optimized for different jobs.
Exactly. You basically hear about two main camps. There's NMC, that's nickel manganese cobalt, and often NCA, nickel cobalt aluminum, goes with it. They're big plus, high energy density. They pack a lot of punch for their weight or their size.
Which means more range in an EV.
Right. More range, or you can store more energy in a smaller grid battery setup. But the downside, they're more expensive. That cobalt and nickel costs a lot. Plus, you've got supply chain issues, sometimes geopolitical ones, and they can run hotter, so you need good cooling systems.
So where do we see those mainly?
Typically in the premium EVs, the high-performance cars. Think of it like Tesla's long-range models. Okay, and the other main type is LFP, lithium iron phosphate. These are, generally speaking, quite a bit cheaper. They're also inherently safer, more stable, especially if things get hot, and they last a really long time, thousands of charge cycles.
Okay. Sounds pretty good. What's the catch?
The main trade-off is lower energy density compared to NMC or NCA.
Ah, so less range for the same size battery pack.
Usually, yeah. Though manufacturers are improving that all the time. But yeah, that's the general picture.
And where are these used?
You find LFP in more budget-friendly EVs. Electric buses are a big one, and definitely in stationary grid batteries. Tesla's standard range cars, for instance, use LFP.
Right. So lithium-ion isn't just one thing. It's dominant because, well, it works. It's proven tech, refined over decades. It is a pretty good balance, cost, safety, energy density, performance. And maybe crucially, there's this huge global supply chain already built around it. But those challenges you mentioned, materials, cost, they've definitely opened the door for what's next. Which brings us nicely to our first rising star, sodium. The big change is right there in the name, swapping lithium for sodium. Seems simple on the surface, maybe, but why does that matter so much? Here's where it gets really interesting.
Oh, it matters hugely. The biggest thing, abundance and cost. Yeah. Sodium is just everywhere. Think saltwater, salt flats. Way, way more abundant than lithium. So it's drastically cheaper to get hold of. And you avoid a lot of the geopolitical knots tied up with lithium and especially cobalt mining.
Okay, cheaper materials. What about inside the battery itself?
The cathodes can use simpler stuff, layered oxide, sure, but also things like Prussian blue compounds.
Prussian blue, like the paint.
Haha, yeah, sounds like it. But here it's a specific crystal structure, based on iron actually. Very stable, great for holding sodium ions, and importantly, really inexpensive to make. Analysts are talking like 20–30% lower cell costs than even LFP once they scale up manufacturing.
Wow, 20–30% cheaper than LFP. That's not small change.
Not at all. It's potentially a game changer. Could really democratize battery power,
Yeah.
Make storage affordable globally and performance-wise. Where are we at? Well, the best cells right now are hitting around, say, 140 to 175 watt-hours per kilogram.
Okay, how does that compare?
So your top-end long-range EVs might be 250, maybe 300 waste kilograms, but 140, 175, that puts sodium-ion right in the ballpark of a lot of today's LFP batteries.
So good enough for city driving, definitely. Grid stuff, too.
Absolutely. Plenty good for that. Plus, they actually handle cold weather better than a lot of lithium types. Good cycle life, good safety profile, too. And the supply chain thing is key. Sodium's everywhere. That means potentially much more stable prices, less geopolitical risk. Big deal for energy independence.
That all sounds incredibly promising on paper. But theory versus reality. Are these things actually being used?
Yeah.
Or are they still stuck in the lab?
No, no, they're definitely moving into the real world. Actually, 2024 and 2025 are pretty big years for deployment. We've already seen the first EVs using sodium-ion hit the roads in China, little micro-EVs, city cars from brands like JC, Hina, Sehol, or Yue, they call them.
Right, so small urban vehicles first.
Yeah.
Makes sense with the cost focus.
Exactly. But also, really importantly for the grid side, China Datang just connected this huge 100 megawatt, 200 megawatt hour sodium ion plant in Hubei. That went online in 2024.
Wow, 200 millimeter battery. That's serious scale.
It's the biggest Naklon storage project in the world right now, a massive proof point. And then there's CATL, world's biggest battery maker, right? They just launched their own sodium-ion brand, Naxtra. They're talking mass production starting December 2025, and they're aiming for around 175 Wh/kg. That basically matches LFP density.
CATL getting in is huge. That signals mainstream intent.
Absolutely. And we're also seeing niche plays like Natron Energy in the U.S. They use that Prussian blue chemistry, targeting data centers, UPS systems. Their focus isn't max energy density. It's ultra-fast charging, crazy long cycle life, things that matter more in those specific industrial jobs.
Okay, so given those strengths, cost, safety, abundance, where does sodium ion really fit best in the, say, near term? Is it going to totally knock out LFP for city cars and storage?
I wouldn't say knock out LFP immediately, but it's definitely positioned as, the economy option, the affordable disruptor. It's a perfect fit for those compact urban EVs, two-wheelers too, where maybe you don't need 400 miles of range, but cost is absolutely critical. And grid storage. Huge potential there. Weight and size aren't the main concerns, but cost per kilowatt hour, safety, durability, sodium ion ticks those boxes really well.
So maybe not taking over the whole EV market yet.
Probably not by 2030. The IEA, the International Energy Agency, they predict maybe less than 10% of EV batteries by then. But for stationary storage, they see it grabbing a really significant growing share. Think about it could unlock much wider use of solar and wind, especially in developing countries. Cheaper storage means you can actually use that renewable power when you need it. Maybe finally get rid of those noisy, dirty diesel generators in off-grid places.
Okay, so sodium ion is the affordable disruptor. That sets the stage nicely for our other rising star. Solid-state lithium. This one feels more like the luxury performance upgrade, the premium future tech. The big difference here, the core idea, is replacing that liquid stuff inside the battery, the electrolyte, with a solid material. Why is that so exciting?
Well, the pitch for solid state, the reason for all the hype, is pretty compelling. Three main things, really. First, potentially much higher energy density, because you can potentially use pure lithium metal for the anode, which is kind of the holy grail. That could mean, say, 30–50% more range for an EV, or make the battery pack much lighter for the same range.
Okay, more range or lighter cars. Big deal. What else?
Faster charging. The potential is there for really quick top-ups. People talk about refuel-like times. Maybe 10 minutes to get 80% charged. Imagine that.
Wow. Okay. That would change the game for EV adoption.
Definitely. And third, safety. Those solid electrolytes, they're generally not flammable. That drastically cuts down the risk of battery fires, thermal runaway, so higher performance and potentially much safer.
Sounds amazing.
Yeah.
Almost too good to be true. What are the catches? Why isn't it everywhere already?
Yes, the hard parts. And they are really hard. One big challenge is preventing dendrites. These are tiny, needle-like growths of lithium that can form over time as you charge and discharge the battery.
And they cause problems.
Big problems. If they grow right through the solid electrolyte, they can short-circuit the cell. Game over. So you need a solid material that stops these dendrites, but also lets lithium ions move through easily. That's a tough balancing act. Maintaining good contact between the solid layers is also tricky.
And manufacturing. I imagine making solid layers is different from liquids.
Totally different. These solid materials, ceramics, glass, special polymers, they can be brittle, hard to handle, hard to make into thin, perfect layers without defects. You often need really high pressure to keep everything tightly packed together inside the cell. It means basically inventing whole new manufacturing processes, building entirely new factories. Like Idemitsu in Japan. They're building this massive plant just to make the lithium sulfide material Toyota needs for their solid-state batteries. It's a huge investment. It's not just swapping out one liquid for one solid.
Right. It's a fundamental shift. So with all that complexity, who's actually making real progress? We hear a lot of buzz, but are there concrete milestones? What's a realistic timeline?
Yeah, it's important to separate the hype from the actual engineering progress, but we are seeing real milestones from major players. Toyota, working with Idemitsu, like I mentioned, they're targeting solid-state batteries for their EVs somewhere in the 2027-2028
Oh,
timeframe.
that's pretty specific.
Nissan's got a pilot line running in Yokohama. They're aiming for commercialization around fiscal year 2028, maybe early 2029. BMW is working with a company called Solid Power. They're already testing large format cells, putting them into actual BMW i7 test cars, not just lab cells.
Putting them in cars. Okay, that's a big step.
And QuantumScape, they're a big name in the U.S. startup space. They've moved to what's called the B sample stage. They're shipping out improved Alpha 2 samples to car makers this year, 2024, and aiming for higher volume samples next year, 2025. These are all necessary steps before mass production.
Okay, so it feels like things are definitely moving, even if it's complex.
They are. So a realistic window, probably 2027 to 2029 for the first commercial EVs from big automakers using solid state. But expect them in limited numbers at first, probably premium models, high-end cars, a broader rollout across more mainstream vehicles. That'll likely stretch into the 2030s as they figure out how to make them cheaper and in huge volumes.
Okay, so let's connect all this back. If we step back and look at the bigger picture, how does this reshuffle the deck? For EVs, for the power grid, it really feels like we're heading towards, I don't know, a more diverse battery world, not just one winner.
Absolutely. That's exactly the right way to think about it. Forget one battery reeling them all. Think of it more like a menu, a battery menu for different needs. You'll still have your nickel-rich lithium-ion, the NMC-NCA types. For the long-range EVs, the performance cars, think, your Tesla Model S long range.
Right, the top tier for range.
Then you've got LFP, that's becoming the mainstream workhorse, reliable, good value, your Tesla Model 3 standard range, lots of other mid-market EVs.
Okay, that makes sense.
Then sodium-ion slots in as the real cost killer, perfect for compact city cars, maybe scooters, two-wheelers, and critically for large-scale grid storage where cost and safety are paramount. We're seeing those first Chinese micro EVs now.
The affordable option.
Exactly. And then solid-state lithium arrives as the premium tech. Top-end range, super fast charging, maybe extra safety bragging rights. It'll likely debut in those luxury or high-performance EVs, probably around that 2027, 2029 timeframe we talked about. So yeah, the key takeaway, no single battery chemistry wins. The future is diversification, different tools for different jobs. That's what the IEA and others are projecting too.
And what about the grid side specifically? How does this diversification help there?
Oh, it's crucial. Integrating renewables like solar and wind, you absolutely need storage. They're intermittent, right? Sun doesn't always shine, wind doesn't always blow. Cheaper, safer storage like sodium-ion promises to be means we can capture way more of that clean energy when it is available and use it later. That Hubei plant in China, the 200 milliliter one, that can power tens of thousands of homes for several hours. That's real infrastructure making a difference now.
And for smaller scale, remote areas.
Huge implications there too. Think microgrids, remote villages. Cheap, safe batteries can finally replace those expensive, polluting diesel generators. They can enable local solar or wind power around the clock to 3037, reduce reliance on imported fuel. That's massive for energy access and resilience.
It really is a powerful vision. Okay, to help everyone keep track of these shifts, let's quickly nail down the most important numbers. What are the key figures you should keep in your head?
Okay, 3 key ones. First, sodium-ion energy density. Remember that range. Roughly 140 to 175 Wei HQRN, puts the newest ones right near LFP, makes them viable. Second, sodium-ion cost. The target, the potential, is 20–30% cheaper than LFP once manufacturing scales up. That's driven by those abundant, cheap materials.
Cheaper materials, cheaper battery. Got it.
And third, solid-state timing. Circle, let's say, 2027 to 2029 on your mental calendar. That's the likely window for the first commercial EVs using solid state. Keep an eye on those years.
Perfect. 140, 175 for neon density, 20–30% cheaper, and 2027, 29 for solid-state EVs. So this all sounds incredibly promising, but this raises an important question. What are the real signals we should be watching for? How do we know these technologies are actually breaking through, moving from promise to, reality on a large scale?
Great question. There are a few clear signals to watch. First, for sodium-ion, keep a really close eye on CATL's next year production. Is it actually starting mass production in December 2025, like they say? That's huge. Also, look for any big sodium-ion projects or factory plans outside of China, a major pilot plant in Europe, the US, India. That would show broader global confidence is building.
Okay, CATL's timeline and projects beyond China. What about solid state?
For solid state, watch for automakers actually showing off demo cars. Not just camouflage test mules, but real cars with solid state packs they're willing to talk about publicly. And, just as important, watch for news from the big chemical and materials companies. Are they announcing or starting construction on large factories specifically to make the solid electrolyte materials? That's the bedrock of the supply chain. That has to happen for mass production. And one more. Linking back to sodium ion and the grid,
Yeah.
watch for large grid storage projects using sodium ion outside China. Anything over, say, 100 milliotors being built in Europe, the US, India, maybe Africa, that would be a very strong signal that the technology is seen as mature, reliable, and cost-effective enough for critical infrastructure globally, not just in the lead market.
Okay, so mass production signals, real demo cars, new material plants, and big grid projects outside the initial lead market. Those are the tangible signs. This is definitely an incredibly exciting space to watch. These battery innovations, they aren't just small tweaks. They really could change everything about energy and transport. It promises a much more diverse, maybe more resilient energy future for all of us. So here's something for you to think about. Which of these battery breakthroughs, the affordable sodium ion or the high-performance solid state, do you think will impact your life most directly in the next 5 years? And why? Something to chew on. Thanks for joining us on the Deep Dive.